And this presentation is not classified. It may be distributed at your will. So if you have any, friends, colleagues, family members who you feel could benefit from this presentation, feel free to do so. I will I'll let you know that this webinar will approximately go about an hour. So hopefully that won't be too much of an issue for you. We do have some great real-time demonstrations all lined up for your enjoyment. So with that said, let me go ahead and get started. So first I must mention both of our companies. Berkeley Nucleonics, we have been in business since 1963. We've grown significantly to where today we have 3 divisions of our company. RF microwave, obviously, test and measurement with all of our pulse generators and etc. The nuclear division, we have personal radiation detectors all the way up to isotope identifiers. Basically, if there is a signal in this world, we would like to provide you the capability to analyze these signals. Now, Pico Technology has also been in the business for quite a while. Now, since 1991, they have been manufacturing high-performance USB instruments. Obviously, oscilloscopes, that is what we will be highlighting today, but they also have data loggers, signal sources, and VNAs going up to 25 gigs. Now, one of the main reasons why we've asked Pico Technology to join us for this webinar is due to the fact that we have similar business models. We understand that the USB-based or PC-control-based instruments are the wave of the future. So it only made sense for us to get together and provide a great webinar, great demonstrations with both of our products working together. Now, a quick tidbit about our worldwide network of sales and service representatives. Now, as you can see in the map, we have pretty much every continent covered. And in the U.S., we have every region covered, from the West Coast to the Midwest to the East Coast. And if you're located anywhere in the world here in the U.S., we're more than happy to connect you to your local representative that can support you on our behalf. Same thing goes for Pico Technology. As you can see, they have pretty much every continent covered, possibly every single country covered. But since we are in America right now, I must mention their North American headquarters located in Tyler, Texas. So you can be rest assured knowing that you will have full support here in local time. Okay, so the agenda for today's webinar. We will be going over budget-conscious instrumentations, the reasons why budget considerations could be important for many users. And then Mark will take over, give us a nice presentation regarding his oscilloscopes, especially his flagship model, the 9400 SXRTO. And then I will come back and give you guys an overview of our high-performing digital delay generators. Edgar will assist while to provide these real-time demos. He is in the lab in the back having all of our equipment hooked up and ready to go. The first model will be the 765. Edgar will give us a nice demonstration of the functions and features. And then I will introduce our video guest from UC Berkeley. Then we'll move on to our 745. Again, Edgar will give a nice demonstration. And finally, I will overview our high-performing arbitrary waveform generators, the models 675 and 676. And of course, again, Edgar will give us a nice demonstration. And finally, we will have the Q&A session. Again, you're more than welcome to type in your question now or during the presentation, or you can wait until the end and we'll definitely address your question. Okay, so let us dive right in. Budget considerations. Now, there are many reasons why a user would care about budget and budget-conscious solutions on the market. We understand not everyone has an unlimited budget, so the first question you must ask yourself is what really matters to you. The cost versus performance factor is very important, right? So, when you're asking yourself these questions, what matters to you? Is this an immediate solution for the application at hand right in front of you? Or possibly you are looking for the future as well, knowing that maybe your application may have some more stringent requirements, higher frequency, etc. It may be good to look at a solution now to prepare for the future. And even with an unlimited budget, the next question may be very important as well. What is the importance of a front panel to your application? Not everyone needs a front panel, and we have learned this over the years, and have developed our product line to be able to provide solutions for these type of needs. And if you do not require a front panel, well, that will already reduce your cost drastically for that same instrument. Remote controlling it obviously is the most important. Having programmable languages being supported, definitely skippy command based, but you may be using LabVIEW, MATLAB, whatever type of software that you're using, or your own software that you have written. We are more than happy to support you. We've also learned that many of the national labs in America are going down this direction, having one specific control room with the specific software to control every piece of equipment in the lab. And in that case, front panel, again, may not be of importance to you. And another benefit of removing the front panel, that will also reduce the size, the form factor of that unit. And that is highly beneficial for people who require integration into their current system. So again, there's many reasons why just a USB-based or a headless design product is attractive. But again, these are the questions that you must ask yourself if that is a viable solution for you or not. Now, I'm going to pass this over to Mark again. He will have in-depth presentation about his oscilloscopes, and Edgar will be ready to give us some real-time demos. So with that said, Mark, let me leave the floor for you.
Thank you, Junior. And let me unwrap for you the PicoScope 9400 SXRTOs, sampler extended real-time oscilloscopes. You're going to need to know what those what the SXRTO is. But first of all, let's just look at some specifications. I've got 5 gigahertz and 16 gigahertz models to talk to you about. Those models sample at up to a terasample per second, or 2.5 terasamples per second. That's down to 400 femtoseconds sampling resolution. And both of them are going to be working with 12-bit ADCs. So we've got high definition, both in time and in amplitude on these two scopes. And then let's draw the attention down to those prices. 14,995 for 5 gigahertz and 19,495 for 16 gigahertz. Yes, I did say 19,495 for 16 gigahertz, not 194,95 that you might reasonably expect for a 16 gigahertz real-time oscilloscope. So, having whetted your appetite with those numbers, let's tell you what a sampler extended real-time oscilloscope is. Next, oh, I need to do the slide, don't I? Let's do that. Okay, so first of all, let's talk about the typical real-time oscilloscope. And my diagram here is of a 5 gigahertz real-time oscilloscope, if it existed. It's a fictitious one. This one has got 4 channels in that diagram on the left there. So the 4 channels at top left. The channels feed a track and hold and an A to D converter. They might be combined into one device. They might not. Each of the channels has a switched gain amplifier. It might have a switched source impedance amplifier as well. And then each of the channels has got a trigger pickoff, those yellow triangles. The trigger pickoffs are sometimes joined by an additional external trigger pickoff. what I want to draw your attention to are the color codings there. I've used bright red to show the very high cost items in a real-time oscilloscope. A duller red to do high cost, and then medium cost orange, and low cost elements are yellow. So you can see there's a heavy bias to high cost items in that scope. In particular, the 20 gigasample per second 8-bit converters, even more expensive if they were 10-bit converters. And then behind that, a very, very high bandwidth data path through to memory. Again, tend to be very expensive, power hungry, real estate hungry elements. As you'll see when we look at an SXRTO, some of those red items come out. Now, down in the bottom right-hand corner, the real-time oscilloscope nearly always has that bright yellow block in the bottom right-hand corner, an equivalent time sampling mode or hardware system. That is used to extend the time-based range or the time resolution for repetitive signals. So extending beyond the transient capture capability of the A to D converters at 20 gigasample per second there. Now, of course, if this was a 16 gigahertz, 40 gigasample per second example, then the cost would increase even more substantially, and certainly it would if it was a 12-bit scope. Whatever the bandwidth, 5 or 16 gigahertz, if this scope existed, it would come from one of those four guys down there. We don't need to name them, you know who they are. Those are the real-time oscilloscope manufacturers above 2 or 3 gigahertz. There is nobody else. Now, just before I go to the SXRTO, I'm going to mention the sequential sampling oscilloscope. Certainly, those of you that are pulse metrologists might well know of the sampling oscilloscope. Now, this is much lower cost instrument. It is an instrument that we make and we sell. There is the PicoScope 9300 that I show there top right. They have much cheaper elements in here. The 5 gigahertz or 16 gigahertz sampling bridge is moderately costly, but not massively expensive. And then behind that, you have really slow A to D converters, quite high resolution, 16-bit, but 1 megasample per second. We're talking audio devices here, aren't we? And if we're only running at 1 megasample per second, the SRAM and the digital backend is all very, very low cost. Now, the thing about a sampling scope is it doesn't have a trigger pickoff on the channels. In fact, it needs a very special trigger. It needs the trigger to occur before the signal that you want to view. And that's because a sampling oscilloscope uses a retriggerable oscillator to do the time base. The oscillator doesn't run until you receive a trigger. You receive a trigger and then it starts running, and a short time after that it can start sampling data. So you can't see the trigger, you can't see pre-trigger, and you need to provide a trigger that leads, ideally leads the signal that you want to sample. So it's a bit clumsy to use. But when you do use it, 16 bits and in our case, 64 femtoseconds of timing resolution, that's a whopping 15 terasample per second acquisition rate, you can get display resolution, waveform resolution way beyond a real-time oscilloscope with a sampling scope. So having mentioned those, let's get to the SXRTO. What's that? How does that work? Well, again, I've got my 4 channels, and this architecture, apart from its color, seems to be very, very similar to a real-time oscilloscope. Notice that it doesn't have the switched gain and switched impedance amplifiers at the front end. They tend to be pretty weak elements in terms of linearity, and they offer they often offer quite poor match to their signal. So the SXRTO doesn't have a switched gain amplifier. It sends its signal directly to a 5 gigahertz track and hold or a 16 gigahertz track and hold. And we use a 50 ohm splitter to get trigger off each of those signal paths. So we've got trigger pickoff, we've got direct feed to the track and hold. Behind that, we've got relatively low cost 12-bit 500 megasample per second A to D converters. And behind that, relatively low cost digital backend and memory. So the architecture is much the same, but we must have lost something. We've lost transient capture rate. We've lost the ability to capture a single trigger event in very high detail. Yeah, it'll still work at 500 megasample per second, so it still works like a real-time oscilloscope, but you're not going to get all the detail you want to see with those A to D converters. But then we go bottom right and we look at that random ETS system with 1 picosecond or 400 femtosecond resolution. We've pushed the random equivalent time sampling mechanism further than any manufacturer has done before, such that the SXRTO can do rather a lot for you at a very, very much reduced price. So for all you pulse metrologists, I thought I'd use this example. So your $19,495 when you buy a 9400-16 SXRTO does all of this. I've got there 4 16 gigahertz of channels, 16 gigahertz channels displayed. The transition time of the measurement is 22 picoseconds when we have bandwidth of that order. All of the channels are being sampled at 2.5 terasamples per second in my screenshot there. And we're able to drive, that image comes straight from a 4K HD display. And we are driving pixel level XY resolution onto that screen. We've got 12 bits and 400 femtoseconds. Do the maths, you'll find out that the resolution is down below pixel resolution in both directions. We can define zoom areas. I think you can see the yellow box highlighting the pulses and the impulse up in the top left-hand corner. Well, the trace below is the zoom of the traces in the yellow box. It's a times 10 zoom. So I'm 1 nanosecond per division at the top. I'm 100 picoseconds per division at the bottom. I've got 25,000 samples on those top traces. I've got 2,500 samples on the bottom trace. So I've got plenty of resolution to see all the detail I want in those waveforms. And what are those waveforms? That's a 50 picosecond rising transition, the yellow trace. The green trace is a 100 picosecond rising impulse. The blue, 50 picosecond falling. The pink, 4 nanosecond rising pulse. And all of these pulses I've defined using delay lines. The reason I did that is I wanted to show you the statistics of the measurement that the scope is making. And if you look at that table beneath, we're measuring rise time, fall time. We're measuring delay between rises of different waveforms. We're measuring pulse width. We're measuring delay between channels. And that right at the end there, you've got standard deviation, and we're down in the 1.1 picosecond to 1.5 picosecond standard deviation on those measurements. And 400 femtoseconds of that is timing resolution in my measurement. So these are extremely high quality measurements. And as I said, without a distorting amplifier there, or distorting match or mismatch of an amplifier, we have very high fidelity waveform and pulse reproduction as well. And for $14,495, you get all of this at 5 gigahertz. You could do all of this as well. You could do data eyes at the input and the output of an amplifier. That's a 1.24 gigabits per second data eye at the top left. I've got a modulation enveloping at 2.4 gigahertz top right. So the blue trace is the envelope of the yellow trace, and I can make standard pulse measurements on that blue trace. So I can get rise time and pulse width, etc., of my 2.4 gigahertz pulse. I can do histogramming and statistics. I'm showing you in the image bottom left, and comprehensive trace maths capability. And the one I've chosen to show you on the right there, that's a 5 gigahertz sine wave, and what I'm doing is trending the width or the period of each sine cycle. So I'm measuring the variation in width as you go across the screen. So you get all of that in an SXRTO. And with that, I'll hand back to Junior.
Thank you very much, Mark. That was great. And again, do appreciate you working with us on this webinar. So as we continue, I must highlight our high-performing timing solutions. And the first one up is our Model 765. This is basically our fastest pulsar in our lineup. We're very, very excited about this. We've had great success over the past year with our customer feedback. Now, this has a spec of 70 picoseconds for the rise and fall times, a very, very short pulse width of 300 pico, but maybe the star specification is the frequency, 800 megahertz. We have a newer update of our Model 765, which increases the frequency from 500 megahertz to 800 megahertz today. Again, Edgar will give us a great demonstration on how to attain this rep rate. He'll show off the rise and fall times, the short pulses. But I must also mention the different models. We have a 2 and 4 channel models, 10 picosecond resolution. The pulse amplitude is about 5 volts peak to peak. But another great feature is the fact that you can attain negative voltage. So it's really 0 to +5 or 0 to -5 volts. Rack mount option is available, of course, if you would like to slide this into your rack system. Now, with that said, Edgar should have the 675 ready to go with the PicoScope. So, Edgar, the floor is yours, sir.
Thank you. I'd like to thank everyone for coming to this webinar, and I'd like to show off some of Berkeley Nucleonics products here. So right here I have them set up. This is the our ARB, and this is the 765 that I'm going to be demoing right now. But I'm also going to show off the 745 as well as our Model 675 later. Now, to do all this, I'm using a PicoScope 9404-16. So that is the 16 gigahertz 12-bit SXRTO. So let's get to the actual demonstration. As you can see, these two units are touchscreen. So I'm going to be remoting in. So you're going to see what would appear on this touchscreen is actually going to, you're going to see live real time. So let me change this here. And you should be seeing my screen. Yep. Okay, so on the screen, I'm generating a basic 50 nanosecond pulse at about 5 megahertz. And it's a 2-volt peak to peak, although I am using attenuators into the scope, so the amplitude won't be exact. I'm currently sampling at 100 gigasamples per second. That's accurate enough for the measurements I'm about to make, but I can up that right here. So let's do 200. As you can see from the bottom here, the measurements I'm doing the rise time, which is, the claim to fame for this, the 765 is the fast rise time. So we spec it 20 to 80% at below 70 picoseconds. And as you can see here, that means like around 60 picoseconds. And it's got a fairly good deviation, jitter, about 6 as well. The width is fairly stable, as you can see, and this is all being done at 5 megahertz. But because we have this extremely short fast rise time, we're able to get a very small pulse width. So let me show you the minimum pulse width. It's about 300 picoseconds. So let me zoom in here, and you can see that. And because we have such a short pulse, and I'd like to point out that the rise time stays the same. So like it's still sub 70 picoseconds. So that's good. And because we have such a short pulse width, I'm able to reach a fairly high frequency. So let me change format here and go to the max, which is 125 megahertz. And as you can see, it's outputting at 125, and you can see it down here too. Another thing about this pulse generator is that it can generate negative pulses. So let me show you that. So here you have the amplitude, but we can change the format and we can set our high point and our low point. So let's set this to 0 and set this to -2. So let me change this to say default, or wait, I gotta change this. Default and this back to 50. Okay, so let me output. Where's it at? And, oh yeah, and down. There it is. Okay, zoom out. You can see it starts at 0 and pulses downward. Let me change the duty cycle so you can see this better to 50%. So square wave. So you can see now we're getting a pulse of negative polarity. So it's baseline 0, negative, around negative. It's outputting -2, but of course I'm using an attenuator. So that is one of the features of the 765 is the negative polarity. One more feature I would like to show you is something we call, it's the pulse mode. And this particular unit has the single pulse, which you're seeing here, double, triple, and quadruple pulse. So I'd like to show you the quadruple pulse. So let me load this to default settings and then load in the saved format here. And let me output. So you can see my quad pulse, and what's over on this screen, you can see it's mimicked over here, and I can change this on the fly. So say pulse 3, I want to increase its width, so I can just do this, and you see in real time that it's increasing. So that's you could do that with double, triple, and quadruple. So the widths and delays are all independently set, so you can delay this however you as well, so it changes. So that's nice. And then we have one capability, as Junior mentioned. Our current revision B has a 800 megahertz max on the quad pulse. So this one I'm using is our first revision, revision A, and it maxes out at 500 megahertz. So let me show that to you. Quad max. Stop that and turn that on and zoom in. And so you can see it's doing our 300 picosecond with pulses, and it's pulsing at 500 megahertz. So those are just some of the capabilities of our 765. And with that, I would like to turn it back over to Junior. And see, he gets his camera going. There he goes.
Yes. So hopefully you guys can hear me. Thank you very much, Edgar. That was great demonstration. And as I mentioned before, we actually have a special guest with a focus application. This application will be regarding ferroelectric switching. Our special guest is Mr. Eric Parsonnet with UC Berkeley in conjunction with Lawrence Berkeley National Labs. Unfortunately, he wasn't able to make the actual webinar today due to a scheduling conflict. So I got together with him a few days ago, was able to record the video. He actually gave us a nice presentation of the application, the setup, and highlighted the reasons why our Model 765 was such a great solution for his application. So with that said, let me introduce Mr. Eric Parsonnet, and I will go ahead and play this video. Please enjoy, everyone.
So yeah, thanks for the introduction. Like you said, I am a physics graduate student at the University of California, Berkeley. I work in the Ramesh lab, and I work with a bunch of other folks who I should mention just because you got to give credit where credit's due. So all of these people here, the Department of Physics, Material Science, also Intel Corporation, and also the Electrical Engineering Computer Science Department at Berkeley. This has been kind of a piece of work between all, a big collaboration with all of those folks. And so today I'm just going to talk a little bit about how I use the 765 model from Berkeley Nucleonics, and specifically pertaining to a paper that I just that we just published called as it pertains to ferroelectric switching. So I'm going to talk a little bit about the physics that we're trying to address or investigate, but I will also highlight, why the 765 was so important. Will it switch screens is the question. There we go. Okay, so ferroelectricity, like I said, I have to give a brief introduction into what the actual physics we're studying is. So what is ferroelectricity? So it's actually a really cool thing. What it is that if I have, can you see my cursor? I don't know.
We sure can.
Okay, great. So what you have is on the left here is this crystal structure. This is a cubic crystal structure, and if in some class of materials, which are called ferroelectrics, if you cool down the temperature of the material, you actually get a phase transition, and you get a distortion in the crystal structure as shown here. And what that means is that the ions that make up the crystal are displaced relative to one another, and you actually get a built-in electric polarization. So as you cool it down, you get the emergence of this P vector, which means that I have an actual electric polarization built into the material. So this is interesting for a number of reasons. Fundamentally, like just from fundamental physics, it's interesting that this occurs. But the reason that folks like Intel or people like that, computer science, is interested in this is because they think that we'll be able to build logic devices basically using this class of materials. So if you want to do that, the reason you can do that is because you can think about this polarization as being basically a state variable. So you could imagine the polarization pointing up, as I've drawn here. That could be a 1, and the polarization pointing down, that could be a 0. Right? So you can actually build kind of logic devices out of this. So that's what a ferroelectric is, and how you manipulate a ferroelectric is by applying an electric field. So it's kind of, that's what I'm showing here in A and B on the right, is as you apply an electric field, so as you apply a voltage to the material, you actually can switch the polarization from up to down. And the way you pick up the switching event is that as I apply some voltage, you can actually, and as the ferroelectric begins to switch, you pick up a current as a displacement current of the actual polarization switching. So here in A, I'm showing basically as I apply some voltage, I can get a current out. And in B, I'm showing that there's this kind of hysteresis behavior. And what I mean by that is, let's say I start in the up state here, and now I apply some negative voltage. I can actually switch my polarization. So the y-axis here is polarization. I'm actually switching my polarization to the negative state. And if I turn off my voltage, I come back here, and my polarization stays in the negative state, right? So in that way, it's a remnant non-volatile state. So after I've switched it, it stays there, right? And that non-volatility and that switching process is kind of the key for building a logic device. Okay, so the thing that I'm particularly interested in, so we're kind of narrowing down here, right? That was the broad overview. Now we're narrowing down to what I'm actually looking at. So what I want to look at is I want to look at the process by which the ferroelectricity, by which the polarization switches from one state to the other. So what I'm going to do is I'm going to apply some electric field in the form of a voltage pulse, and I'm going to watch the current that comes out of the material to understand how does that switching process actually occur. So this is the type of experiment I'm doing here, and I have a little animation that I think will explain things a little bit. So the red balls are synced together. So let's just say that I'm going to basically trace out this hysteresis loop. So what I'll do is I'll apply some negative voltage, and that will preset my polarization in a well-defined state. So by applying that negative voltage, I preset my polarization to the negative state. Now I apply a sequence of 2 up pulses. The first up pulse will switch the polarization. I'll let it relax to what I called the remnant state, if you remember. and then I'll drive it again with an identical up pulse, which will not switch the polarization, but will enable me to look at how the material responds when there is no switch, right? So the key here is that in the first up pulse, switching response plus some other kind of dielectric or just other types of material responses, and in the second pulse, I only have the material or the non-switching response. So what I can do is I can subtract the response to the first pulse minus the response to the second pulse, and that gives me just the switching response. Okay. So what you can do is you can do this. This is what it actually looks like. So this is kind of in B here. I'm showing what it looks like for that. This black line shows the switching response plus the non-switching response. And this kind of gray line, which is a little bit hidden, that shows you the only the non-switching response. And so what you can do is you can subtract the two, and then you get something like in C, and that's purely switching. All right, so that's what we're trying to get at. We're trying to understand what is the process by which the polarization goes from up to down, and we do it by looking at this sequence of 3 pulses. One presets the polarization in a well-defined state. The second switches and measures the rest of the circuit, basically. And the second one measures only what's happening in the circuit, not the switching. And so by subtracting the two, you can get just the switching. Okay, so this data I'm showing here on the bottom is actually from a different paper. And I want to highlight that the time scale is relatively long, especially with what I'm going to show you guys in a minute here. So this is in the microseconds. But there has been some work done which used a kind of complex device structure. So I'm going to talk about what this is. So one of the reasons that that this was such a long time scale is because the stimulus is relatively slow. So what I mean by that is if I'm applying, just some pulse generator, and I'm capable of, let's say 100 nanosecond rise times, then nothing is going to happen faster than 100 nanoseconds because that's the rate at which the stimulus is being applied. So one way to get around this is to do something pretty intense, and takes a lot of microfabrication steps. This is a little bit complex, but all they do here is this is basically just a pulse generator. But the way that they do the pulse generator is they use a laser pulse in order to create a very short rise time, pulse. So by biasing kind of this, I can bias across these two contacts, and then I can shine a short laser pulse as shown here. And what that does is it kind of photo excites carriers, meaning that I can get a very short lifetime of voltage pulse that comes down the pulse generator. So you can do this, but it's a lot of fab steps, and each time that you want to do one switching experiment, you would need to make an entire device like this, which is very involved and not something that we wanted to do because we want to be testing a lot of different devices of different geometries and different materials, et cetera, et cetera. So we don't want to have to be going through the step of making this kind of laser pulse generator every single time. So the reason I show this is because they showed some very interesting data using one of these laser pulse generators. And what they found was that you can get switching. So this is the same exact experiment I explained before, where you subtract the switching minus the non-switching response. And they found that you can get switching of your ferroelectric polarization in the kind of hundreds of picoseconds. Okay, so that was much faster from that microsecond time regime that I showed you earlier. And the question is this kind of ubiquitous across different to all ferroelectrics, or was it just a kind of something that happened in this experiment only? And so what we wanted to do is we wanted to answer that question. We want to say, all right, can we see things happen at this kind of time scale? But we don't want to have to go through all those fabrication steps, and that's kind of where the 765 comes in, right? So something that's relatively, and can get us, honestly, relatively close to these kinds of timescales, but doesn't have to be all of this fabrication and kind of time-intensive work. So what did I do? There's a lot on the screen. This is directly from my paper. So what I do is I actually use this pulse generator here is the 765, and I basically just use I run the voltage pulse into my material. So that's right. I think I showed you earlier. You have a top electrode, a bottom electrode, and you have the material. And that's exactly what I have here. And I just use the 765 to generate my voltage pulses. And what I find is I can get switching in the tens of nanoseconds. That's in here. And this is kind of where we're starting to scratch the surface of we're approaching those much faster timescales. So now we're 2 orders of magnitude faster than that 1 microsecond sort of timescale. And what's really interesting about so what's really interesting is that without the 765, we would have never been able to reach these timescales, right? So I used it in order to apply the stimulus in order to look at the switching event, and was able to actually kind of get to the fastest timescales observed in this particular material, this LBFO here. But more importantly, it was, I can now take what I've built and I can go do a very simple fabrication process, and I can test a whole plethora of samples much faster than this kind of fabrication process. So, right, the keys to the 765 were, this really fast rise time. That's the thing that I really cared about the most, because that basically defines what's the speed limit of my stimulus. It's computer programmable. The switchable polarity. This allows me to do my pulse profile where I have a preset pulse and then 2 up pulses. It's very reliable. Everything I needed was it worked every single time, and I had very fine control over the delays of the 2 pulses and the pulse widths and that sort of thing, which is all very important. I haven't quite gotten into all the details, but it's all very important when it comes to looking at how these things switch. And the kind of key takeaway from my paper, which is something that had never been, which is what really made it novel, was that because of this really fast stimulus, what we were able to do is we were able to look at devices of various geometries and start to disentangle what is happening because of the device itself and like the geometry of the device itself, and what's happening because of the intrinsic switching of the polarization. And the only way we were able to get to this, only way we were able to understand this, is because we were no longer really limited only by the stimulus time, right? So by going to small devices and using the 765, we were able to see switching down in like the single nanoseconds, which was something that had never been seen before, and allowed us to kind of intuition or new understanding of how does the actual geometry of the device and the intrinsic physics of the ferroelectric switching from one state to the other, how do those two kind of interact? And that is like what the kind of novel piece was that we actually were able to get out of it. And it wouldn't have been possible if we hadn't had the fast rise time and the ability to apply the correct pulse profiles. That's pretty much my slides. I obviously want to thank everybody I worked with, especially my Professor Ramesh. But yeah, I'm happy to go into more detail. I just kind of wanted to give a brief overview and explain why the 765 was so essential. It was really, just to summarize, it was really because we wanted to get to very fast stimuli, and without having to go through this huge fabrication process, it's just literally a plug and play. I can just take it into my lab and plug it in, and then I have what I need. And it actually gave us some really cool insight. I'm happy to talk more about the insight or whatever, but I think that's a relatively short, quick overview of what we did. Does that make sense?
It sure does, and that's quite amazing, actually. And just to reiterate, for the 765, is that fast rise time. It was the polarity, being able to choose between negative and positive. And then being able to fine tune the pulse with the delays. And, I'm very, very glad to hear this. And you guys are doing some groundbreaking stuff,
Yeah.
Okay. Well, I hope you guys enjoyed the video. I did notice a little bit of choppy audio, but I think for the most part, all the information was there. And again, Eric is more than happy to discuss with you more about his application. If there is interest, any other students out there maybe doing something similar, I can get you connected with him, not a problem. So let me continue. We are, nearing the finish line here. Since we talked about fast pulses, fast rise times, now we must talk about our low jitter solutions. That brings us to our model 745. And the two images that you see there, we have two versions of this model. We have the 20 channel. That is an image you see on the top. All the outputs are in the rear of the instrument. The image below is our small benchtop unit. There's a 4 and 8 channel versions of that. And the specs are very, very good. Now, back to the 20 channel, you can actually have two units in a slave master configuration. You can have literally up to 40 channels with two boxes stacked on top of each other. Resolution for that 20 channel unit is 1 picosecond. Accuracy is very good as well at 250 pico. The jitter from external trigger to output is about 25 picos, but if you're using the internal trigger, you'll see much better numbers. I'll show you that in just 1 second. Voltage is all within TTL range, but you do have options to get higher, up to 32 volts, and many memory storage slots for you for many different settings that you have already saved. So the difference between these two models, right? I mentioned 1 picosecond resolution for the 20 channel, but for the benchtop 745T, you can even attain a better resolution, 0.25, all in the femtosecond range, which is quite amazing. The range is very good as well, going up to 20 seconds. Jitter, as mentioned before, using the internal trigger, you can attain 5 picoseconds versus the 25 for the external trigger. Accuracy stays the same for both units. Now, I have these three specs listed here: resolution, range, jitter, and accuracy, as these are quite the most important specs that you would want to take a look at for high performance, high precision timing solutions. So with that said, let me hand it back over to Edgar so he can show you, especially the jitter specification of the 745 using the PicoScope once more. So Edgar, the floor is yours.
They're muted. Okay. Thank you. I'm going to be using the benchtop model, as you can see here. It can be remoted in, and you can use the web address using its IP address. But I've already set it up, so that's like the quickest way to do that. So I'm going to switch this over to my screen, and you can see the PicoScope over here. And I'm just doing a simple 2 channels. So channel 1, the yellow, is TO. That's coming out of the back of the unit. And then channel 2 is our channel A. So as you can see, I am measuring the delay, the rise time, from TO to channel 2 or channel A. And you can see the jitter is a little bit below the 5 picoseconds, and that's where we spec it at. So that's nice. One thing I'd like to point out, though, is this actually has a fairly fast rise time. So it's spec'd at sub 1 nanosecond with 50 ohms. Yeah. So as you can see from this, it's below 1 nanosecond. And I'm doing these measurements with the PicoScope because you can, like I said earlier, you can change the actual sampling rate. So I am getting a 2 picosecond resolution. So that's pretty much all I wanted to show you on the 745, because this is like the bread and butter. The low jitter is like, if you're looking for that, this is what you want. So with that, I'd like to turn it back over to Junior.
Okay, thank you for that quick demo, Edgar. So, we talk about, timing solutions and the importance of high precision. Well, usually it will be needed in laser system applications. Now, I pulled up a slide here, a quick visual of what a typical laser system would look like. Now, in order to attain the best precision, you'll most likely need an external clock, in this case an oscillator at 80 megahertz. and each one of your devices will be synced to that clock. And in this case, if you look at the chart, you know what? Let me pull up my pointer here so you guys can follow where I'm looking at. So if you can see, hopefully, my apologies. Okay, so we're going to have to make do with the little red dots that I'm going to make on this chart here, but just wanted to quickly demonstrate, the different components that will go into a laser system here. So you have your master clock at 80 megahertz. This will be synchronized with every single device within the setup. As you can see, there are 2 amplifiers with some components within each amplifier to gain that energy, increase that energy, transfer that over with a laser pump. All of these devices, again, will be connected to the timing system, in this case, potentially the Model 745. And from there, you can set each device to trigger at your certain parameter. It will usually be a single shot target. And this is where the experiment will happen. Your laser will output to your target. You will see the results. You will be able to detect those results and then be able to analyze those results. And again, this is just a typical laser system visual, but again, the application can increase. The complexity can increase with the large area timing systems. Now, the majority of these national labs in the country, they have large area timing systems with a very high-powered laser. So in this case, most likely they will probably require optical fiber connections instead of BNC cables. And that will give you much better precision, much better stable signal. Now, we can provide you solutions in that area as well. Please don't think that all of our instruments are just off the shelf. We have the ability to customize to your exact specification, your exact needs, especially for these large area timing systems. So if you are currently with one of these national labs or even a private company that is working with large area, please let us know. We're happy to provide some support for you. So we're nearing the end here. We're almost at the finish line. I just must quickly go over our high-performing arbitrary waveform generators. And let me close up this little window here. You probably can't see it. So this, we're very excited about this as well. This is very similar in terms of the form factor, the functionality of the Model 765 fast pulsar we just showed you. Now, in this case, very high performing. Again, as you can see, the resolution is 2.5 gigasamples. You have a range of channel options. You have 2 analog, up to 8 analog channels, 32 digital channels, very low, spurious-free dynamic range at minus 60 dB. The 675 is our lower frequency model. It has a frequency of 300 megahertz. The 676 can get you up to 1 gigahertz, which is great, but must also mention the rise and fall time in the pulse mode. The 765 we mentioned, it can provide you 70 picoseconds. Well, with our arbitrary waveform generator, you can adjust the rise and fall time to 800 pico up to 800 nano, which is still very, very great specs. Now, with that said, I know Edgar is hooking up our 675 unit right now. Hopefully he is ready. Edgar, let me pass it over to you. If you can quickly give us a demonstration before I finally talk about our 685.
Alrighty, so I'm going to switch over my screen. It's hooked up now to our PicoScope. So let's see, where's my screen? There we go. And as you can see, I'm just generating on channel 2 here. It's just simple waveforms, a sine wave, but there's a lot of preset waveforms in this. So as you can see, we got sine, square, ramp, and I can run those as well. You can see it generates the square wave. Pulse. So it has a lot of built-in functions. One thing I would like to show you though is, let me set this back to sine wave real quick. Okay. and I'm going to show you the modulation. Turn that off. So here I'm using just a sine wave as my carrier, and it's about 100 kilohertz frequency. But I'm setting the modulating frequency to 10K, so because it's linked with my channel 2 to trigger to keep it stable. So as you can see here, it's just a basic AM modulation, but this has lots of different types of modulations. Oh, this is AM. Yeah, there you go. That was FSK. Sorry, this is the AM. So as you can see, it has different types of modulations. This is AM. We saw FSK, and it also has obviously FM if it has SFK or FSK. Yeah. So there's a lot of things I could show you on this, but I'm just gonna go through a lot of the different things because this is a very robust system. So I'm gonna switch over to a different software on this. I'm going to switch to the TrueArb. Now, these things are Windows 10 based, so they're essentially they're computers by all respects. So it has the desktop, it has storage, and it has all that. It even has internet connection. So there's different options you can get for these. The last one I'll show you is an option. It's the pattern generator, or this is the pattern generator. Yeah, here we go. So this is one of the options we can have. Let me output this. Yes. Let me zoom in. And as you can see, I'm just generating a basic ramp type pulse. The thing with this is you can change the transitions. So right now it's ramp up, but I can change it to exponential rise and exponential decay. As we go over here, you can see it's changed, and you can see real time it's changed as well. So, and that is capable of going up to multiple points or multiple transition data. I'm just showing you this one because it's simpler to show. Another one of the apps on this is the TrueArb writer. So let me load that up. And you can see all the apps on the desktop there. Like I said, this is essentially a computer. You can even hook up a mouse keyboard monitor to this and use it as a computer. Like instead of like remoting in, like you can do it that way as well. But everything you see here is also shown on the touch screen. So that is a nice function, and it's a very, very good touch screen. Like if I didn't have to do the demo, I'd probably be using the touch screen. So here we have the sequence generator, which is another thing I really like about this. Now let me turn this on. Yes. I'll try to show you the sequence. It's kind of hard to get it. And there we go. And let me zoom out. So you can see it I've slowed it down a little bit so you can see the actual transition here. So it's generating a Gaussian into a sine and into a ramp, and you can change all these. Turn it off. So right here, and it has all the presets. So you can do a square wave, and then hit it, and you see it goes through the sequence again: square wave, sine wave, ramp. There's one last thing I'd like to show you, and I believe that is in. Let me close this software. Actually, it is the waveform editor. So this is capable of generating a multitude of arbitrary waveforms, and you're able to input your own functions, points. Like if you have a list from like Excel, you're able to the time points and amplitude points. So like here I'm generating a sine wave, but I can customize that and change point by point. So like I said, I could spend probably hours demoing this, but I'm hitting the quick points here for you guys. One thing I would like to point out, a lot of these things wouldn't even be possible to be shown without the PicoScope because, let me show this thing to you real quick. For everything you've seen it do, look at it. It weighs like a pound. It feels sturdy, and it's barely even hot. So like you could stack these things in like a rack, 10 of them at a time. So, it's all remote. So, that's just, if you really want a really accurate PicoScope, especially if you're like using our like pulse generators and stuff like that to really see what they're capable of, this is what you want to do. And with that, I'd like to turn it back over to Junior.
Thank you very much for that, Edgar. So, yes, that was our Model 675. And again, if you have arbitrary waveform needs, any specific applications, we're more than happy to help you. And please reach out to us directly, and we will provide that support. Now, finally, Want to introduce our upcoming Model 685. Brand new. We should have this model available by the end of the year. We actually should have the first demo unit available for our customers within the next couple of weeks. And again, if you have a need for high-performing ARBs and would like to try one out, please do let us know. But let me quickly go over what you will see with this unit. Same amount of channel options. You have 2, 4, or 8 analog channels, able to have 32 digital channels. The resolution, so from 2.5 on our 675 and 676, it has jumped up significantly to 6.16 gigasamples. And I think technically, this may be the fastest arbitrary waveform generator in the world. Now the bandwidth, again, we are doubling it from 1 gigahertz to 2 gigs. The offsets will stay the same. The amplitude will stay the same as well at 5 volts peak to peak. And you have many memory points to save. Now, this is a very high performing ARBs. We have a full line. And I want to quickly mention quantum computing and how these ARBs can be of solution for your quantum computing application. Now, this is just a basic visual, again, of how a QC application can be set up. If you look right in the middle here, the PXI chassis, that would be your signals, the different components for your signals. So, you definitely will require an arbitrary waveform generator that will cover the base band of 500 megahertz. Now, in our case, we have the 685 I just mentioned going up to 2 gigs. We have the 676 going up to a gig. Those two units can provide your baseband IQ modulated signal. Now, IQ, I know Edgar had shown you the different modulation examples, but IQ can be attained by synchronizing 2 outputs out of 1 unit using a modulator to combine those. You can have your IQ signal going to the mixer. So for the AWG portion of your setup and the signals that you require, the 685, the 676, those 2 units can provide a great solution for you. Now for the LO, the local oscillators, the RF signals, we also have our 855 multi-channel RF signal generators, going all the way up to 40 gigs. So these are very popular as well for quantum computing applications. All of the outputs are phase coherent. So again, we, instead of looking for an all-in-one solution for every piece of equipment from one manufacturer, you do have some alternatives out there, and we can provide some great instruments to help you. Now, I just wanted to quickly mention quantum computing because this is a focus that we will, for future webinars, that we will focus on in the coming months. So I believe, I would say January, keep an eye out for our next webinar. Again, this will be strictly about quantum computing, about our different solutions and how they can be of a solution for you. And most likely you will get an invitation within the next month on when this webinar will happen. So that pretty much almost wraps it up for us. Final mention here is our BNC Academy. I think many of you are already aware this is something that we started earlier in this year. Great success. We have many courses now available for all of our customers, whether it's RF fundamentals, with phase noise measurements, signal timing and triggering with our pulse generators, and our high precision timing, nuclear courses as well. Obviously that might not fit into what your expertise is in right now, but hey, if you wanted to learn a little bit more about the nuclear industry and those type of applications, that is all there for you. And normally we do have a small charge to attain these courses, but since you have taken the time to join us today for this webinar, I would like to offer every one of these courses to you completely free. So as you can see, this is the address, the web address to attain the online classes, to get to the courses. Your code is just the word Berkeley. You type that in in the credit card portion of the page there. It'll completely reduce your cost to zero, and all the courses will be there for you. Now, the only thing that we ask in return is that if you do take the course, you do use this code, that you give us some good feedback. You know, we're continually trying to improve these courses. Currently, some universities around the country are actually making this a requirement for some of their curriculum. So we'd love to see this increase, but we can't do this without your feedback. You know, so if you see some content there that could be improved, or you would like to see some better visuals, please do let us know. We would highly appreciate that. So that pretty much does it. That is the end of our presentation. Again, thank you very much for joining us today. I guess we can open up the gates for the question and answer period. So, and I've noticed that lots of questions that we're typing in during the webinar. Please feel free to ask us some more questions right now, and if you'd like, I will unmute your microphone if you wanted to ask us verbally.
Yeah, I saw Dax was answering questions throughout, and I think Mark was as well. So
yeah. So maybe that might be good for questions. And if we missed you, or if you think of a question down the line, please feel free to reach out to us directly. You know, you can email us at info@berkeleynucleonics.com. You can check out Pico Technology at picotech.com, picotech.com. You can give us a call. You can even email me directly. My email address is just junior, JUNIOR, at berkeleynucleonics.com. All of us are more than happy to work with you to answer any questions that you may have, and let us know your pain points with your application. We may be able to customize a solution for you. So, you know what? I see some people typing right now. So before we sign off, maybe we can answer one more question. Oh no, it was just a comment. Thank you very much, Mostafa, for the feedback. Appreciate it. Emily as well. Jeff Glaze, thank you. And I will say thank you to some names that I do recognize in the attendees. You know, Mr. Dave Cloyne, you know I love you. Correctly going through Guillermo, you know, very great customer coming to all of our webinars. And yeah, thank you so much. Appreciate it. I guess it's time we can sign off. But again, we will send you this recording to you shortly after we sign off right now. Thank you very much, everyone. Bye-bye.